All right, I want to take a look at an actual proof of a limit. Okay, that is, I want to look at the limit, a pretty simple one. The limit as x goes to, let's say, 3 of 2x plus 1. Right? What do you think the limit is? Well, I think the limit is 7. Okay? And how did I get that? I mean, I didn't use any epsilons and deltas. This is a pretty nice function. What happens as you get close to 3 is pretty much the same thing as happens when you get to 3. Well, when you plug a 3 in there, you get 2 times 3 is 6 plus 1 is 7. Well, that's where my 7 came from. Right? So calculating the limit has nothing to do with epsilons and deltas. Now, proving that I'm right, here's where the epsilons and deltas come in. Okay. Now, in the problems at the beginning of the homework section in the book, they they keep giving you deltas. Sorry, they give you epsilons as they find delta. I want to do that, and then I'll set up the the proof here. And the thing is, I'm going to work the whole problem backwards. We want to end with that the absolute value of f of x minus L, so 2x plus 1 minus 7, that's my f of x minus L. I want that to be less than epsilon, whatever epsilon I choose, right? In fact, for every epsilon I choose, I need to be able to do this. So I'm looking at this inequality, and I'm saying, all right, let me see what that tells me about the x values. This 2x plus 1 is a y value, and then this minus 7 is the other y value. And so here we go. How do we get this? I'm going to simplify that inside parentheses there, inside the absolute value. So I've got absolute value of 2x minus 6 is less than epsilon. Notice for absolute values, over on the side here, if I just had the absolute value of x is less than, pick a random number here, 7, you're looking at an absolute value function, and you say, when is that less than 7? Right, here's 7. Well, it's less than 7 in between -7 and 7. So when I'm looking at this thing, saying this absolute value less than epsilon, when is that less than epsilon? Well, when this number, 2x minus 6, if it's less than epsilon, right, that would be like playing the role of 7 here, or if it's bigger than negative epsilon, right? So I need this thing, 2x minus 6, to be somewhere between minus epsilon and plus epsilon, so that when I take the absolute value will be less than epsilon. Now I'm going to figure out what x values here are important. So actually I'm going to do this 2 different ways, but let's add 6 to both sides here. So 2x is less than, sorry, bigger than, and less than, and divide everything by 2. So I've got x is between 3 minus epsilon over 2 and 3 plus epsilon over 2. Actually, this is now really nice, because if you think about what we were doing before, when you gave me a particular epsilon, I'd find the lowest x I'm interested in and the highest x I'm interested in. Well, because this is a straight line, something really nice happened. Here's 3. I'm saying the x's that are good are from 3 minus epsilon over 2 up to 3 plus epsilon over 2. Now to figure delta, I had to figure out what's the distance here, what's the distance there, and take the smaller one. Well, it turns out these distances are the same. This epsilon over 2 is already, that's the distance. The distance that you go forward or backwards is epsilon divided by 2. And so that's what I want to let delta equal, epsilon divided by 2. Notice it's the epsilon divided by the slope, if the slope was 2. So now I'm ready to do the proof, right? And the proofs look very similar all the time, because you're trying to show that the definition is satisfied. And the definition is a very specific type of statement. It is a for each epsilon statement. How do you prove something's true for each epsilon? How would I prove that it's true that, all dogs bark? Do I have to go and look at every single dang dog and say, hey, bark, woof, bark, woof? You don't want to do it specifically. You want to do it in general. You say, pick a dog, any dog. Don't tell me what dog it is, and then somehow I've got to be able to show that the characteristic of being a dog will imply that the thing barks. All right. Um, so this is what I do. Same thing. I need to show that for each epsilon something happens. So I'm going to just say let epsilon be bigger than 0. I'm essentially saying pick an epsilon, any epsilon. Don't tell me what it is. All you've told me is that it's bigger than 0. Okay. Now I'm going to make a definition here, and I'm going to say let delta equal epsilon divided by 2. That was my calculation I did here. Okay. The thing is, what do I need to show for, what is it in the definition about epsilon? What do I have to do for each epsilon bigger than 0? I have to show that there exists a delta such that something happens. Okay. So I need to show that delta exists. Well, here's my delta. You tell me what epsilon you want. I'm giving you delta. Epsilon divided by 2. Okay. What do I need to show about delta? I need to show that if x is in this range, then f of x will be close to L. How close to L? Well, no more than epsilon. So there's an if-then statement in that definition, right? The definition says if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. So I need to show that this if-then statement is true. You've given me an epsilon. I've said here's the delta. I need to show that for this delta, this statement is true. Okay. Now, see, this is a thing that I think is crazy. In some ways, I think that a prereq for this class should be a logic class, because, I mean, when have you ever proven an if-then statement? We haven't done that yet. So how do you prove an if-then statement? Well, the way you prove an if-then statement is you say, assume the first part is true, and then show that the last part has to be true. So if this is true, then that has to be true. Okay? So here we go. My first step of the proof is let epsilon equal 0. Second step is let delta equal whatever I calculated up here, right? I mean, for each function, it's going to be a little different as to what you calculate your epsilon, your delta to be. So that, and then you say, assume that the absolute value of, so that 0 is less than the absolute value of x minus, what am I approaching? 3, right? X was the value I was approaching. That x minus 3 is less than delta, right? So if that's the case, then the absolute value of x minus 3 is less than epsilon over 2, right? Because I'm just replacing my delta with epsilon over 2. This is equivalent to, actually multiply both sides by 2. So I've got 2 times the absolute value of x minus 3 is less than epsilon. Distribute the 2 inside there. So that's the absolute value of 2x minus 6 is less than epsilon. And all of a sudden I'm starting to see, wait a minute, I was here before. I was here before. Because at this stage here, but where'd that come from? That came from here. So let's work that backwards and just say, okay, this is now 2x plus 1 minus 7. Is that what I had? I'm sorry, I've forgotten already. 2x plus 1 minus 7, yeah. All right, is less than epsilon. Notice this right here is the f of x. This right here is the L. And what I have is that I assumed that x minus 3 in absolute value is less than delta, and I end up with f of x minus L is less than epsilon. For each epsilon bigger than 0, I have a delta such that if this is true, then that's true. I've satisfied the definition. I've shown that, yes, I do have the limit. Therefore, 7 is the limit as x goes to 3 of x cubed minus 3x plus 4. They all look this. They're all very similar looking proofs. Let epsilon be bigger than 0. Figure out what delta is. You've already done that up above. You've done some work. You say let delta be that, and then you assume this thing's true, and you work. Essentially, I'm working these steps backwards to get back to this. Right? The calculations I did above was I started with this and I got down to here, essentially, and now I'm coming back. Unless you're going to be a math major, you're probably never going to have to do an epsilon delta proof in your life. So this is not a big part of this class. In fact, once we move away from section 2.4, you'll probably not see an epsilon and delta for the rest of this course. So if this is not gelling with you, that's fine. If you think you're going to be a math major and you want to look into this a little more in depth, then by all means, ask me some questions, and we'll look at some other examples. There's a few examples in the problem sets from the book that they ask you to do this. I'm really only interested in the linear ones for now, and delta will always be epsilon divided by the slope. But once you get into more abstract mathematics, then you'll come back to looking at these epsilon delta proofs and using them in other situations as well. Okay. But for now, I want just to expose you to them.